Welcome and hello. This is a video tutorial in HEC RAS, and in this lesson, I'm going to be discussing unsteady flow simulation options. There are a lot of options, so in fact, this may even be a two-part video depending on how many options I can get to in this lesson. So let's go ahead and get started. What I have on the screen here is my HEC RAS. There's my files up above, my geometric data I have open down below. And then what I'm going to be talking about in this lesson is if you go to Run, Unsteady Flow Analysis, Options. As you can see, there's a number of different options here that we're going to be talking about in this lesson. All right, so another way to open up this unsteady flow analysis dialog box is to click on this button here with the stick figure that's running uphill, and then boom, here are the options once again. I will leave a link to the user's manual page right here that discusses all the unsteady flow simulation options in the description of this video if you want to read for yourself and get more detail. All right, so let's go ahead and get started. The first option is stage and flow output locations. So right now I already have one selected. I'm going to deselect that by double clicking. And let me just do a before and after because I was prepping for this lesson. That's why there was one already selected. When we run a simulation and then click the compute button, like I just did, what it's going to generate is a DSS file. So let me go ahead and open that file up in DSS view. So go open, navigate to the DSS file, and then open. And by default, it's going to provide a cross-section data for the downstream end of the reach, which is river station 0, and the upstream end of the reach, which is river station 2000. But so I got a flow hydrograph, a stage hydrograph for both of those. But say, for instance, I wanted to get a flow or stage hydrograph for some intermediate cross-section. So for instance, this 1000 river station cross section. What I would do is I'd go into the options, stage and flow output, and then select any one of these river stations. So let's go ahead and do 600 and 1200. So I'll double click those, or you can just click them once and then click the arrow button and then click OK. And then let's rerun that simulation. So it's doing the same thing again. All right, so that's done. I'll click close. Now I have that same DSS file open here, so all I need to do is go view, refresh catalog, and now we have a few paths for flow and stage hydrograph for both the 1200 record and the 600 river station cross section is what those are. So I'm not going to get into the details of that. Of course, there's other ways to view results as well. I'm just trying to make this as quick and easy as possible to demonstrate this particular feature. All right, below that is the flow roughness factor, and I'm also going to include in this discussion the seasonal roughness factor. These two roughness factors multiply the existing Manning's N roughness by a factor, typically a value close to 1, so it's not a huge difference from original. I'll click on flow roughness factor right now, and what it's going to do is as the flow changes, that roughness factor may change as well. Typically, the higher flows and the deeper depths indicating higher flows result in a lower Manning's N roughness factor. So the first step we would do here is click on plus RS, which is to add a new river station. So I'll select the river, select the reach, and then select the upstream and downstream end. I'll just say it's the entire reach, so from 2000 all the way down to 0, and then click OK. One thing to keep in mind is you can't have overlapping flow roughness factors. You can't have a range that goes from 2000 down to 600 and then another range from 1000 down to 0 because then you'd have 400 feet of overlap. Okay, so what we can do is just manually type in numbers here like 0, say 1,000, 10,000, okay, something like that. And then the roughness factor I'd say is 1.2, 1.11, 0.9. Okay, so as the flow increases, that roughness factor that's set in the geometric data would be multiplied by this roughness factor here in the plan data. Another way to do that is to use these buttons to set the data automatically. So I'm going to zero out that data. And then for uniform spacing, for instance, or exponential increasing, uniform spacing says I start at a certain value like 0, and then the uniform spacing would increase, we'll say 1,000 CFS, and then that will happen for 4 different rows. So I guess that'd be 0 up to 3,000, generate flows and cancel. Yeah, so it just automatically populates this flow column as a way to save a little bit of time. That's what that uniform spacing does. And then if I wanted to use the exponentially increasing value, let me see if I start here. I would start a value. So I'll say it starts at 100. We'll say it increases by 10, and then that goes for 4. So up to 100,000, generate flows. So now I've auto-populated the flows from 100 up to 100,000. I'm not a big fan of this because I would like to start at 0, but you could probably cut and paste or something like that. I'm not going to even try it. If you have a separate range, so for instance, if you wanted to just do from 2,000 down to 1,000, you would go ahead and set that range. Oops, I guess you have to set that range at the beginning. So I'd have to delete it, set the range, and then you could add a new river station from 1,000 down to 0. One other warning I want to make mention that the user manual also mentions is, let me delete that. Okay, so that's how we get back to normal. But these flow roughness factors can also be defined in the geometric data editor. So this is in the plan data, and that's fine. You can define it anywhere you want. But that interface should look familiar if I go to geometric data editor, tools, flow roughness factor, and look what we have here. Now it just says geometry up here, but it would basically apply the exact same user interface and flow roughness factors. So you got to remember not to double up and apply those changes both in the geometry data and the plan data. It's probably best to just stick to one. All right, so back to the unsteady flow analysis options. Seasonal roughness factor, same thing. This also exists in the geometry data. So make sure to only apply this once, if at all. But what you're going to do is go ahead and select the river, and then select the reach, and then select the range. So maybe it's only for 1,000 down to 0, that range there. After that, you go ahead and add in your roughness factors. You just type those values in here. So for instance, in the winter time, there may be higher roughness and then maybe less roughness as the water heats up. Well, it's really more about the channel itself, but that's how that works there. Okay, so I'm going to just cancel that out. All right, next in the options, we have automated roughness calibration and automated flow optimization. So automated roughness calibration right here. The automated calibration procedure computes adjustments in existing flow roughness factors to follow observed stages. So basically what this is a way to automatically create those adjustment factors that we were just entering manually. This topic is a little bit beyond what I want to talk about in this introduction topic of just unsteady flow options. In fact, I probably will have a separate lesson on just this topic alone, but I should probably mention that for to use this feature here, you must already have in the geometry or plan data observed stages and unsteady flow data before implementing this calibration procedure. So we just saw what the flow roughness factors are already, so we want to get those as close as possible by just manually entering data and then testing it. And then the second requirement here is observed stages must already be set in the unsteady flow data. So where that is if I click cancel and then edit unsteady flow data. Now, if you click on this observed data tab, we have observed stages right here. So we'd have records for the different specific cross sections that we're trying to match the calculated water surface elevation or stage with the observed data. So to do that, we would select the river station. We'll say maybe 1,000, add it. So that's there. Okay. And then here we can edit and river station 1,000. And then we would select our method, either DSS, table, or constant. Okay. Anyway, a little bit too much detail, but just let you know that that information is available in Chapter 16, Advanced Features for Unsteady Flow Routing in the HEC RAS User's Manual. Here is the user's manual once again. I'm going to just zoom to the screenshot of what I'm talking about here. This is the user's manual screenshot of that same dialog box. The next option down in unsteady flow analysis is automated flow optimization. Just like the automated roughness calibration, it's a little bit too involved for this lesson, but I'll have another lesson covering these topics in the future. All right. Next up is unsteady encroachments. Encroachments refers to the restriction or reductions in the available flow area of a river or channel cross section due to human or natural factors such as levees, flood walls, embankments, and other obstructions. So what we're going to do here is select a base plan for encroachment. And I've already created an original plan, like a base plan with no encroachments, and then an encroachment plan. So I'm going to save two separate plans here, but I'm going to select my lesson 828. This is the base plan file that I'm going to base my encroachments off of. Down below that, we have this table here where I'm going to select the river, select the reach, and then type in the method 1 through 5, and then type in the data underneath that method's column. So for instance, if I wanted to make an encroachment here for River Station, the cross section at River Station 1000, and I wanted to use method 1, I would type a 1 in here, and now the columns for method 1 have now become enabled. And say, for instance, the station left and station right values are 300 and 700. So what that looks like is basically there'd be no overbank. Let me go to that cross section real quick. Yeah, so 300 is here and 700 is here. So I'm basically creating an encroachment so there's no overbank area at this particular river station cross section at 1,000 feet. Okay, so let me go back here. And I think that's how it works. The user's manual doesn't provide an updated version. I think it's a little bit out of date because this right here is the screenshot for unsteady encroachments. And it doesn't talk about method 1, 2, 3, 4, 5. I guess it does say method 1 right here, but it doesn't give any information besides what you're seeing on the screenshot and a little bit of text right here. So go ahead and check that out and read it for yourself if you're curious, but I was just giving an introduction to the topic right here in this video. The user manual does also mention that you can click this button to get encroachment from steady flow plan data. When this button is pressed, the user is asked to select a previously computed steady flow plan and a specific profile from that plan. So for instance, I would select just lesson 28, and then these right here are the different times. So it's a 24-hour period. So these are just 3-hour increments for the first day of the year. So I could just, for instance, start with the midnight time, the very first time period. When the user presses OK, the program will go and get the final computed encroachments from that particular steady flow plan and profile. Yeah, so it's asking if I'm sure. I'm going to say yes and just see what happens. And because that original plan didn't have any encroachments, you're seeing no data right here. Okay, so I do plan to do an exercise with encroachments later. That is an interesting topic. Back to unsteady flow options. I'm going to select options, and then next up is ungaged lateral inflows. This is another one I'm going to defer to later. It's a little bit too involved for this lesson, but what it does, it allows you to calculate the inflow from an ungaged source of water. So for instance, flow coming in through a lateral structure can be calculated by simply subtracting the upstream flow of that lateral structure from the flow downstream of that lateral structure, and then the difference would be the flow contributing to the main channel from that lateral structure, or vice versa. You can see how much water is leaving through that lateral structure. So what you do is click New. You would say Area 1, for instance, and then you would select, say, two different options. Here, you'd have either Add Lateral Inflow, and this would be at one specific cross-section, or you'd say Add Uniform Lateral Inflow, and this would be a range between two different cross-sections you would select. And then there are some additional tools up here, which a little bit too detailed, but just let you know that there is a way to use HEC RAS to compute ungaged lateral inflows. So options. The next three is something we're also going to discuss in a later lesson, but dam breach, levee breach, and storage area connection breach. So we're just going to leave those behind right now and then spend the rest of this lesson talking about computational options and tolerances. So if you open up this dialog box, you can see we have a lot going on here. There's a number of tabs across the top, starting with general, 2D flow options, pipe systems, and so on. We're going to focus on general for the rest of this lesson and then have time for the others in later lessons. These computation options and tolerances allow the user to set some computation options and override HEC RAS default settings. The first values here is theta and theta for warm-up. The default here is 1, but you can see the range is 0.6 to 1, 0.6 to 1. Theta deals with the solution accuracy. zero point 0.6 would be the most accurate, but it's also susceptible to instabilities. And then 1, which is where it is right now, that is the most stable, but not necessarily the most accurate. The next field down is water surface calculation tolerance right here. It has a maximum value of 0.2 feet, and then a default value here you can see of 0.02 feet. When the difference between the computed and assumed water surface elevation is larger than this tolerance right here that the user enters, then HEC RAS continues to iterate. Otherwise, HEC RAS will assume it has a valid solution. So this is about tolerance and convergence criteria. The next one down is storage area elevation tolerance, maximum value of 0.2, and then default value of 0.02. This is basically the same thing as the water surface calculation tolerance, except it is for storage areas. Below that, we have a couple more tolerance values. There's the flow calculation tolerance. That's optional. This is sort of like the water surface elevation, but instead of stage or elevation, it is the flow rate. So if the flow difference exceeds that user entered tolerance flow rate, then HEC RAS will continue to iterate. And then this one here, max air in water surface solution, abort tolerance 100. This option allows the user to set a maximum water surface air that will cause the program to stop running if it is exceeded. So if the water surface is ever over 100 in my particular model, and it shouldn't be, then the model will quit, regardless of which iteration it's on. Which brings me to my next two, maximum number of iterations, 0 to 40 is the range. The default value is 20, as you can see there. That's pretty self-explanatory. It's the number of iterations the maximum number of iterations that HEC RAS will run. Of course, if tolerance is met before the maximum, then it will stop whenever that convergence criteria is satisfied. Maximum iterations without improvement. So the example they provided was 5, and what that means is if 5 iterations take place and there's no improvement at all the computation nodes, then HEC RAS will stop computing, even if that maximum number has not been reached yet. And the reason being, maybe computations take a long time and all hope is lost of any improvement if you can go this 5 or whatever maximum number of iterations without any improvement. You might as well just quit. And then the final result is not the final value, but rather the best value, so that HEC RAS will go back to the best previous iterations value and return those numbers. Okay, over here in the right column, 1D, 2D unsteady flow options, number of warm-up time steps, it says 0 to 100,000. And then the user manual says 0 to 200. So I think the user manual is actually outdated in a number of ways. So I would just, if there's a difference, I would look at the screenshot and what the software is telling you. Warm-up time steps help make a more stable solution at the beginning of the simulation. So to be safe, you can add some time steps during warm-up period. So if it's set to 0, this is going to basically use the same time step as the actual simulation, but it may be advantageous to use a smaller time step during that warm-up period. So for instance, if the simulation is using a 1-hour time step, you may want to use a time step that's less than an hour, like 0.5 or 0.1 or something like that. Okay, I'm just going to set it back to 0 though. By the way, if you ever want to reset all your values back to the defaults, there's this button here in the bottom right, defaults. So let me change this to 0.5 and change this to 50 and then click defaults. And then, yep, just the confirmation. And the original values are now reset. All right, the minimum time step for slicing and the maximum number of time slices. These two refer to the boundary conditions. So if you remember from the previous lesson, if there's a very dramatic and fast increase in the flow rate that would cause instability, then the boundary conditions are sometimes spliced to basically, instead of one time step, it's divided into 2 equal time steps where the change in flow is half as much in both time steps. This value right here allows the users to set a minimum time step for slicing, as well as the maximum number of time slices. I assume 0 for the minimum time step means that there is no minimum. Okay, the next 1, 2, 3, 4 values all are similar. The range is between 1.0 and 3.0, and it deals with stability factor and decay exponent. So it's lateral structure, flow stability factor, inline structure, flow stability factor. weir flow submergence gate exponent, and gate flow submergence decay exponent. Basically, the value of 1 is the default. Oh, I guess it might be 2 here. Okay, no, it's 2 here. The default values you're seeing right here. 1 basically means it's more stable but less accurate, and then 3, excuse me, is the most accurate but the least stable. If results from your simulation are oscillating, first of all, try decreasing the time step in the computations. But if you've done that and the time step is sufficiently small, then the user's manual says to increase these flow stability factors from whatever they are up to a number closer to 3 or 3 itself. The gravitational constant is right there. That's probably something you should leave as it is. And then over here on the left, we have wind forces, both reference frame and drag formulation. So the reference frame, our options are Eulerian and Lagrangian. I would use Lagrangian. What this is talking about is when calculating the net speed of the air over the water, the user must select between one of these two methods, where Eulerian doesn't take into account the vector of the water itself. It just uses a fixed point. And then the Lagrangian method does take into account the speed and the direction of the water when calculating the difference in speed between the wind and the water. Drag formulation is below that, and this is where the user selects one of the different drag coefficients, or if you, this last option here is a constant. So if you want to type in your own constant drag coefficient, you can do that, or use one of the 4 methods described here. There's more information on these 4 different methods in the HEC RAS hydraulic reference manual. The geometry preprocessor option right here, the default is the first option to use the internal boundary tables when possible. Those are the hydraulic tables that are calculated when we first use the geometry preprocessor step right here. That will save time and processing power. But there's also an option to recompute at all internal boundaries. So this would take longer, but the user may have a reason to perform these recomputations each time. And the last frame in this first tab of general is the 1D numerical solutions. The default selection here is finite difference method, specifically skyline Gaussian, which is for faster dendritic systems apparently. But there's a few other options as well, including this finite volume method. It's in a beta, which has its own pros and cons. And the user manual actually goes on for a long time discussing the different pros and cons for this finite volume method. So go ahead and read more up on that in the user's manual, which I'll link in the description of this video if you're interested. Okay, well, that's a long enough video. I wanted to keep these a little bit shorter, but what we did is we talked about the different options for simulation of unsteady flow. So from HEC RAS, we clicked on Run Unsteady Flow Analysis, and then we talked about the first options here from stage and flow output locations all the way down to computation options and tolerances, specifically this first general tab.